Okay, we're going to look at section 4.6 now. This is applications of our exponential growth and decay model, and I kind of hinted on one of these a little bit earlier when we were talking about exponential growth and decay models earlier, okay? So our formula is going to be y equals y naught e to the kt. Okay, now k is going to be constant, and one of the things that we know here is if k is positive, it's growth, and if k is negative, then it's decay, or it's getting smaller, okay? So this is a nice, lovely little consistent thing that's going to happen when we happen to be in this particular model. Now, what's going to happen with these is they are going to give you a starter value, they're going to give you an ending value, and you're going to have a time. And the first thing that you're going to have to do is solve that equation to get k. And so when we do that, okay, so for example, the one we're going to look at here as an example is they tell us that in 1990, we had 353 parts per million in carbon dioxide, okay? Now, I'm going to use, if I use the year 2275, they tell us that there will be 2,000, okay? So they want us to now figure out what this exponential equation is going to be that gives us this, okay? So the way that we do this is using our y equals y naught e to the kt. This is going to be y naught. This is going to be your starter value. Now, from here to here is 285. That's going to be t. And then for purposes of the starter example, this is y. So I've got 2,000 equals 353 e to the k times 285. Okay, so we're going to divide the 353 off. So we've got this. Now I'm going to take natural log on both sides. And again, natural log and e cancel each other off. Okay. So now we've got, bring this down. Natural log of 2,000 divided by 353 equals 285k. And then we're going to divide by 285. So I'm going to line up with natural log of 2,000 over 353 over 285 equals k. Now, putting all of that on calculator, I get that k is 0.006. Okay, so now my equation, when I go to repull my equation up, okay, I'm going to come back up here to the top, sorry. We're still going to consistently use that 353 number, 0.006t. Okay, so this is now our equation that we are going to use, okay, for anything that they would ask us to do. Now, they're going to ask one of two questions. They're either going to say, predict what it would be in year whatever, okay? And that would be going here for t. Now then, if they are using the other thing they'll ask is they'll give you a secondary amount. So like, for example, this one asks, when will it double 280? Well, double of 280 is 560. So now again, we're going to solve for t. Now this is going to feel very, very similar to the other problem that we just did because it utilizes the same steps. Okay, so natural log of 560 divided by 353. Okay, and then divide that by our 0.006. We get that T is 76.91. Now keep in mind, since we started out as this is our initial thing, this was 1990. Okay, so when we started out with that equation, 353 e to the 0.006 t, okay, this was a 1990 amount. That means this is time after 1990. So if we add 1990 to this, we get that that's going to be 2066.9. We probably call it 2067. Okay, is when we would estimate that that would hit 580. Now, in the PowerPoint, they show a table that went along with this, and they showed that in 2075 it was 590, and we were trying to go to 560. So that kind of fits inside of that time frame for what's happening there. Now, the next one asks how long it will take. Okay, how long will it take for money that is at 3% continuous interest okay, to double? Okay, now everybody always has a problem when they don't give me a dollar amount. Fine. First off, formula that we're using for continuous interest is A equals PE raised to the RT. Guys, put dollar amounts in here, okay? Just make sure something doubles, okay? I'm going to say I started with $100, so I'm trying to go to $200, okay? Now, they will often try to say, this is 2P and that's P and whatever. I really don't give a care, okay? As long as you're doing a starter amount and they want it to double, okay? Put dollar amounts in there that make sense for you. So, again, first thing we're going to do is divide, because what's going to happen is I don't care if you put 1,000 and 2,000 or 500 and 1,000. As soon as you divide over, you're going to get this equation, okay? Even if they did something like P and 2P, as soon as you divide off, you still wind up with this equation. This is the meat of where we're trying to get to. So again, I'm going to put natural log on both sides because I am working with E. So I want to make sure that I'm getting those nice, pretty cross-offs that are going to happen there. So now I've got natural log of 2 equals 0.03t. We're going to divide by that 0.03. Now, this is a scenario, guys, where you do not need to give an exact answer like this, okay? You don't walk up to somebody at the bank, or you don't go into the bank and ask them, how long is it going to take for my money to double if I'm at 3% continuous interest? It's going to take natural log of 2 divided by 0.03 years. That's not the way that works, okay? Like, give an actual answer. So we get that T is 23.1, and this would be in years, okay? Now, the next one, okay, that they give us, okay, and for this one, they were talking about the world population reached 6 billion people in 1999 and continued to grow exponentially. By the end of 2010, it had grown to 6.947 billion, okay? And so they gave us an equation that looks like F of T, that's the same thing as Y, y'all. 0.00745 T. And T is years after 2010. Okay, so they asked, what is the population going to be in 2020? Guys, this is just a straight plug-in. This is going to be that T is 10 because 2020 is 10 years after 2010. So this is 6.947 e to the 0.00745 times 10. Guys, that is a straight calculator plug. There is nothing special about that one. Okay, and we get the 7.484 based on the fact that they did 3 decimal places here. I did 3 decimal places here. So that is the estimate for 2020. Okay, Now, they can do the same thing where they ask, when will it reach a particular amount? 8 billion, 9 billion, whatever. You're going to plug that in, and that is the same method that we have seen solved beforehand, okay? Now, the other spot that this is used, and this is used more in the decay, is we talk about half-life stuff, okay? Every chemical has what's called a half-life, and it is the amount of time that it takes half of the stuff to go away. So, for example, if I started out with 100 grams of something, if we go one half-life, I've got 50, okay? Now, if I go another one half-life, it's half of this amount, so it's going to put us at 25. Guys, it is not just half and then the other half. It is half of what we currently had. So if I went from 100 down to 50, I'm now going from 50 to 25. And then from 25, we would go to 12.5, and so on and so forth, okay? So here is the statement that they make for this next question, okay? We've got 600 grams of some sort of a radioactive substance that are present starting. 3 years later, we've got 300 grams, okay? So it asks us to determine a growth model for this. So using our y equals y naught e to the kt formula, we start off. Now, you got to watch it on these, okay? This is your starting amount. So that's got to go there. I'm ending with the 300. And then I've got this. So dividing underneath, we're going to have 0.5 equals e to the 3k. We're going to get natural log on both sides. And guys, you should start to realize that we are following some of the same steps every time we're doing these. Okay, so we've got natural log of 0.5 divided by 3 is going to give us negative 0.231. Okay, is what I'm going to use. Now, first off, this makes sense because I said if K is negative, you are decaying. Sure enough, that's what I've got. Now, they can then ask, so now if I come back up, okay, and I'm going to rewrite my equation now. Again, I'm starting with 600, e to the negative 0.231 t. So there's now my equation. They ask how much will be present after, I don't know, we're going to pick something here, 7 years. Okay, now, guys, here's the deal. If they had asked, because this is obviously a half-life, we went from 600 to 300, that's half. So 3 years is its half-life. If they asked me to do something like 6 years, well, if 3 years I had this half, another 3 years, another half-life, it'd be 150, okay? So we're going to look at what it is if I wind up on some kind of in-between marker. 0.231 times 7. So now, one of the things that we should recognize is that since this is past the 6 year mark, I should be underneath half of this, okay? So I should be under 150. And we get that this is 119.096, okay? And so sure enough, we are up underneath that, okay? Now, one of the spots that gets used often with this half-life stuff is carbon dating, okay? So they look at particularly carbon-14, okay? That is the particular carbon format that they look at for carbon dating. And they have hashed out and they give us that the formula for that half-life okay, for carbon is negative 0.0001216 T. Now notice again, they haven't given us amounts here. Okay, this is where we're talking about the original. Now, it asks us to find what the half-life is, like how long is that duration. So again, knowing that a half-life is half, pick something that's an easy number. 100 is an easy number. Half of it is 50. Okay, so we're going to divide by 100. This is looking eerily familiar. And again, here we go with natural log and E. And again, the whole point of using natural log with E is so that we can do that cross out. And then we're going to do natural log of 0.5 divided by that lovely big old decimal number. And we get that T is basically 5,700, okay? So it's about 5,700 years, okay? Now, one of the other things that they will ask, okay, and I'm going to bring this back up to here, is they will say something like, an item has 30% of the carbon that it started with. And everybody always goes, but I don't know how to do it. Fine. Pick those numbers again. 100 is wonderful. 30% of 100 is 30. Okay. Make your life easy by picking numbers that you can easily track with. Okay. So again, we're going to divide through. This is going to give us 0.3 this time. And here we go, bringing in natural log again. So we've got natural log of 0.3, negative 0.0001216t, dividing. Okay. We get that T is 9901, basically. So this is how old that object is, okay? Now then, one of the things that you should know about when they do carbon dating and stuff, it is very difficult to know exactly what percentage is there or exactly how, I mean, they can measure the amount that they have now, but it's very difficult to know what the starting amount was because we may not have a comparable modern age thing. So, for example, if we were doing like a woolly mammoth, similar in size to some of our current elephants, but we may not have the correct scale up for that, okay? Again, it may be very difficult to know the exact percentage or the exact amount that's coming out of this other part, okay? Look at another one, okay? Hopefully my lovely is going to. This example is Newton's law of cooling. This is one that all the little CSI shows use, okay, when they okay, not sure what happened there, okay, really not sure, okay, so Newton's law basically says if you put like let's say a hot cup of coffee into into a room, okay, that has the air conditioning on, as the coffee sits there, it's going to start to cool off, okay? And so that's what Newton's law of cooling says, is now the coffee, the temperature of the coffee is never going to get lower than what's in the room, okay? So we see this with the CSI stuff when you have a body that's supposed to be 98.6 degrees roughly, okay? And they're in an air-conditioned room or they're outside or whatever else. They can go through and figure out based on body temp that they have currently and the ambient space around it, the ambient temperature around it, they can figure out how long that body's been there, okay? Because they know how things are going to process and go down, okay? So here we go. Our formula for this okay. T naught is the temperature in the environment. Okay, so this is like the temperature of the room. C is a constant, and K is also a constant in this. Okay, so it says a pot of coffee with a temperature of 100 degrees is set down in a room with a temperature of 20 degrees. The coffee cools to 60 degrees after an hour, okay? So it says write the equation. Now, guys, if you remember seeing this, okay, this looks very much like our set up normal thing that we have, okay? So what we've got is, okay, so the room temperature was 20, so it's going to go here. This is your starting temperature. So this is the 100-degree pot of coffee, okay? And this was in Celsius, y'all, okay? So this was all Celsius stuff. And it says we're getting down to 60 in 1 hour. So I'm going to do stuff in hours here, okay? Now, so first thing I'm going to do is subtract my 20. Okay, that's just going to be negative K up there. I'm going to divide by 100. I'm going to get natural log running in here. So natural log of 0.4 equals negative K. So negative natural log of 0.4 is K. So I've got K is 0.9163. We'll use that. Okay. So now I'm going to rewrite my equation. Okay. So the difference is going to be back up here at this original thing, 0.9163 T. I'm also going to get rid of this side. Okay. So then it says find the temperature after half an hour. Okay. Now, y'all, you've got to be careful with that. Because we did this in time was in hours. So this needs for half an hour, that needs to be 0.5. So this is a straight plug-in, again, straight to a calculator. And we get that this is 83.25, okay, and that would be degrees Celsius, okay. And then they ask, another question they ask is, how long will it take for us to get to 50 degrees, okay? This one is going to be very, very similar to the one where we pulled, it went down to 60 degrees after an hour. Now, the other thing, knowing that it went to 60 degrees in an hour, okay, and we're going down to 50, this better be longer than an hour, okay? So again, we're going to subtract the 20. Divide, that's going to give me 0.3. I'm going to bring natural log in. And then I'm going to divide by negative 0.9163. So natural log of 0.3 divided by negative 0.9163 gives me that time is 1.314. So an hour, almost an hour and a third. Okay, so an hour and 20 minutes. Okay. Now, if you wanted to get something into, if they asked for you to do stuff in minutes, then the original where we did 1 up here for our time when we were figuring out K, that would then need to be 60. Okay, so just kind of depend upon how accurate they want that to be. So there is section 4.6.